Range is hot, clear for launch.
DARPA's Fast Lightweight Autonomy, or FLA program, is advancing technology to enable small, unmanned quadcopters to fly autonomously through cluttered buildings and obstacle-strewn environments at fast speeds, up to 20 meters per second, or 45 miles an hour, using onboard cameras and sensors as eyes and smart algorithms to self-navigate. FLA could someday help troops or civilian rescue crews safely scan for threats or for people in need of help inside buildings when entering those structures could be unsafe. Phase 1 of DARPA's FLA program concluded recently following a series of obstacle course flight tests in Central Florida. Over 4 days, 3 teams of DARPA-supported researchers fine-tuned the code they'd uploaded onto their sensor-laden quadcopters before and after each run during FLA Flight Test Experiment 4. These tests built on previous flight experiments, challenging the team's abilities to develop algorithms that would allow their unmanned aerial vehicles, or UAVs, to self-navigate and find a target, in this case a red barrel, and return to the starting point. The environments were difficult and varied. In one location, UAVs had to sense and avoid trees and Spanish moss in a wooded area. In another, the UAVs had to find their way into a hangar through an open door, then navigate inside even as bright sunshine gave way to a dark obstacle course. In another test, these environments were combined as the UAVs made their way out of thick woods, crossed a bright aircraft parking area, made their way into the hangar, maneuvered around obstacles, found their target, and made the trek in reverse back to the starting point. Teams used an assortment of sensors and approaches to accomplish these tasks, but it was what they weren't using that made these tests revolutionary.
Today's operation requires a constant link between the airplane and the user. That link can be very fragile, can be jammed, can be hijacked. It also tells other people that something is going on, so it's not always desirable to have this. It also requires a trained operator. GPS is also very vulnerable. It's a very low power signal that is very easily jammed. It is lost when you go inside a building or under the ground, or even sometime in deep urban canyons, you will not get a good GPS quality. So really removing those two things, the GPS as an aid and the RF link, is really what the vision of the program was, to enable fully autonomous capability from takeoff through the whole mission all the way back to landing.
The only human input that would be needed is a description of the target or objective, which could be in the form of a digital photograph uploaded to the UAV's onboard computer before flight, and the bearing and range to that objective, that is, the compass heading and distance to the target. A basic map of the area, if available, could also be uploaded. After the operator gives the launch command, the vehicle would navigate its way to the objective with no a priori knowledge of the terrain or environment, autonomously maneuvering around obstacles in its way and developing alternative routes as needed. The task proved challenging, but the results were impressive, with each team showing strengths and weaknesses on the different courses based on the sensors they chose and the way their algorithms and onboard computers tackled navigation in an unknown environment.
We're really focused on the algorithm in FLA, which means that eventually they can be moved on any type of platform. To date, we are putting them in general purpose computers or sometimes graphic processor units, but that's really where we are pushing next, is to reduce the size of the computing needed to do that for small vehicles.
In Phase 2 of FLA, teams will further refine their systems and build on the valuable lessons learned in Phase 1.